Hey guys, today's lesson is all about the different definitions of acids and bases. So essentially all the different ways that we describe what is an acid and what is a base. So you will have to know the different properties of acids and bases, as well as how Arrhenius defined acids and bases and why there were some issues with that, what the modified Arrhenius definition is, and then you also need to be able to write both Arrhenius and modified Arrhenius equations, as well as write conjugate acid and base pairs. So the empirical definition is just all the different observations that people have made over the centuries about acids and bases. So these observations have been made both through experimentation and through the senses. And empirical definitions are just the summaries of all of these properties of acids and bases. So acids are described as turning litmus red. So litmus paper is a pH indicating paper. All acids will turn it red. Acids are always electrolytes as well because they break apart into hydrogen ions and a negative ion when in solution. And because they're electrolytes, they will conduct electricity in solution. Acids taste sour, though you should never actually test that out in a lab. They will neutralize bases. They will react with active metals to produce hydrogen gas. They will react with carbonate compounds to produce carbon dioxide, and they will be corrosive to both metals and organic substances, meaning that they can kind of eat through metals as well as organic substances like your skin or any other living thing. Bases are a little bit different. They will turn litmus paper blue instead of red. They are also electrolytic, so they will also break apart into ions and therefore conduct electricity in solution. They will taste bitter instead of sour. They will neutralize acids. They will feel slippery like soap. They are corrosive to organic material, but not metal. And they're also called alkaline. So if you hear the term alkaline, it usually refers to something that is basic. Neutral substances are just substances that aren't acidic or basic, so they will have no effect on litmus paper. Some of them will be electrolytic and some of them won't, usually based on whether or not they're ionic. And therefore they may or may not conduct electricity, and they have no characteristic taste or feel. The Arrhenius definition of acids and bases is that acids will dissociate to produce hydrogen ions in solution, and bases will dissociate to produce hydroxide ions in solution. So just a reminder, when we say that something is dissociating, we're saying that it is just breaking apart into the two separate ions that make up that substance. This definition actually doesn't work very well because you never just find hydrogen ions floating around by themselves in solution. Instead, we see the creation of hydronium ions, which are H3O+, not just an H+. And that's because the hydrogen ion that is released from the acid bonds to a water molecule, specifically the slightly negative end of the water molecule. And the other issue is not as big of a problem. Some bases will dissociate to produce hydroxide ions. However, not all bases contain a hydroxide ion, and therefore they won't all dissociate to make an hydroxide ion. So for example, ammonia, NH3, is a base, and yet it doesn't contain an OH and therefore cannot just split in half to produce an OH. The Arrhenius equations are essentially you just take the acid or base and you dissociate it, you split it in half. So your Arrhenius equations are essentially going to look identical to a dissociation equation. However, they're not correct. That's not what actually happens. Acids do not dissociate at all. And while this Arrhenius equation is correct for sodium hydroxide, because sodium hydroxide does dissociate, some bases don't. bases that don't contain an OH already will not be able to dissociate. So that's where the modified Arrhenius definition comes in. It's sometimes called the revised Arrhenius definition, also sometimes called the Bronsted-Lowry definition, because those were the guys who came up with the modified Arrhenius definition. This definition takes into account the fact that hydronium ions are formed by acids, not hydrogen ions. It also explains the behavior of bases that don't contain an OH, like ammonia. Instead, it defines acids as substances that donate protons. So it says that acids are proton donors, which just means that they give up an H plus to the water. And it also says that they will react with the water to produce hydronium ions, that H3O plus. Bases are defined as proton acceptors, meaning that they will take an H plus from the water. Because of that, they're also defined as producing hydroxide ions in water, though sometimes this will be a dissociation, like with the Arrhenius equation, and sometimes it will be an ionization reaction. So if you're writing modified Arrhenius equations or Bronsted-Lowry equations, these equations are going to contain water. All acids will have a modified Arrhenius reaction, and any base that does not have OH will have a modified Arrhenius equation. Bases that have an OH will not have a modified Arrhenius equation. In this case, with modified Arrhenius equations, the water is actually participating in the reaction. And so the water will either gain a proton from the acid or it will lose a proton to a base. There will always be a hydronium ion produced if the reactant was an acid, or a hydroxide ion produced if the reactant was a base. Okay, so in this case here, we have hydrochloric acid reacting with water to create a hydronium ion and a chlorine ion. So this is just the ionization reaction for hydrochloric acid. So anytime I say Arrhenius equation, what I'm really saying is write the dissociation for the substance. If I ask for the modified Arrhenius equation, I'm asking for the ionization equation. Next up, we have ammonia here. So ammonia is a base. It will react with water. Because it's a base, it's going to produce a hydroxide ion. And then because bases are proton acceptors, it is going to get an extra H plus. NaOH, or any base that already contains an OH, will not ionize, it dissociates instead. So it just splits in two, the same way any ionic compound would. Okay, conjugate acid-base pairs are pairs of acids and bases that are only different by one H plus, or one proton. So the base will have one less H plus than the acid, or an acid will have one more H plus than the base. So for instance, H2CO3 and HCO3 minus are a conjugate acid-base pair. The H2CO3 has an extra H compared to the HCO3 minus. So that makes the H2CO3 the conjugate acid and the HCO3 minus the conjugate base. And then lastly, we have the theoretical definition of acids and bases. Essentially, it is just comparing the amount of hydronium and hydroxide ions in solution, as well as the pH of acids and bases. So acids will always have a higher concentration of hydronium ions Bases will have a higher concentration of hydroxide ions. Acids will have a pH below 7. Bases will have a pH above 7. And if the pH is right at 7, it is neutral, and that substance would have an equal concentration of hydronium and hydroxide ions. So those would just cancel each other out, and you'd have a neutral substance. Okay, what I'm going to go through now is just a couple examples of some of these equations and identifying your conjugate acid-base pairs. Okay, so this is just a summary of the different types of reactions that affect acids and bases. So you have the Arrhenius equation here, which is when we take our acid and we just dissociate it. So we just break it apart into the two different ions. This works the exact same way as dissociation reactions work for ionic substances, where we just take our ionic substance and break it apart into the two ions. With an Arrhenius equation, we take our acid and break it apart into a hydrogen ion and a chlorine ion in this case, or a hydrogen ion and then whatever the other metal, or sorry, non-metal is. Bases that have an OH will also dissociate, and their Arrhenius equations will be the same thing as their dissociations. So we just take our base and we split it apart into our metal ion and our hydroxide ion. And again, the Arrhenius equation for a base is identical to its dissociation. Bases like this actually dissociate. Acids do not dissociate. That is why this Arrhenius definition for an acid does not work. And so that's where the modified Arrhenius comes in. The modified Arrhenius is just an ionization reaction. It works for weak bases or any base that does not have an OH and all acids. For any type of ionization reaction or modified Arrhenius, you always have to have water as one of your reactants. If it's a base, you'll take your base, add the water. Because a base is a proton acceptor, it's going to get an extra H+, and it always makes a hydroxide ion in solution. When an acid reacts with water, the acid is a proton donor, so it gives an H+ to the water, which is how we make our hydronium ion, and then our non-metal becomes the other ion. Now, anytime you're looking at conjugate acid-base pairs, you're always looking at the modified Arrhenius reaction or the ionization reaction. So we'll start by identifying our actual acid and actual base. So NH3 is a base, and OH is always a base. And then when we're trying to identify our acids, well, if we call this base 1, our acid that goes with this base will have one extra proton or one extra H+. So this has one extra H+ from that base, so this becomes acid 1. So they are a conjugate acid-base pair. If this then is base 2, well, H2O has one extra H+ compared to OH, so that makes our H2O acid 2. So water and hydroxide are an acid-base pair. We look at the very last reaction here. Hydrochloric acid is definitely an acid, and hydronium ions are always an acid. If I call this acid 1, acids will always have an extra H+ compared to the conjugate base. This hydrochloric acid has an extra H+ compared to the chlorine ion, so that makes the chlorine ion our base. And then water has one less hydrogen than our H3O+. So if H3O+ is acid 2, that makes water base 2. You'll see that depending on whether we are ionizing a base or an acid, water can be either a conjugate acid or a conjugate base. It just depends on whether we're making a hydroxide or a hydronium ion. If we make a hydroxide ion, that is our base, water is its conjugate acid. If we make a hydronium ion, water is its conjugate base.